So I was challenged today by my teacher, um, on I guess whether I could come up with a decent explanation and proof for the L'Hopital's rule. And um, so I did so, but I had to do so in my government class where I only had around 40 minutes to do so. Um, and yeah, probably around 20 minutes total. So I did have a lot of time to focus, I guess, after I finish my work. But anyways, disregarding that, um, I don't know if these proofs are mathematically correct. But note that I came up with these myself, but I didn't come up with the method myself. Is I guess what I'm saying. I knew before that the L'Hopital's rule was derived using the Cauchy's mean value theorem. Um, but I didn't see the proof. I don't know the proof, so I don't know if these are correct. But I did show my teacher, and he says that mathematically they follow. So let's go over the indeterminate form 0 over 0. That would mean that limit as x approaches c of f of x over g of x, where f of c is equal to 0 and g of c is equal to 0 would be indeterminate. But notice we can just rewrite that as f of x minus f of c over g of x minus g of c. But this looks really familiar. This looks like derivative definition. So we can rewrite this as f of x minus f of c divided by x minus c over g of x minus g of c divided by x minus c, because these simply cancel out. So that was pretty simple. We just proved that it's f prime of x over g prime of x. Or I guess you could say f prime of c would be the better definition, simply because the derivative takes on this value. So now we get to something interesting. And that proof was pretty simple. I hope it's correct, because, um, it's whatever. My book uses the values C and X. So I hope someone can tell me if that's wrong, because I think that followed mathematically perfectly. But now we get to infinities, and this is where I kind of had to um, where I kind of had to take a longer thinking process. So my first thought process was, if I take the limit as x approaches infinity of f of x over g of x, where they both approach infinity as x approaches infinity, that I could kind of do a trick like last one, where I add f minus c. In fact, I added I think I added plus 1 over, or no, yeah, I put 1 over g of x, because as g of x is approaching infinity, this is equal to 0. And then I did something like 1 over f of x, where since these are both going to infinity, these are going to 0, so these are the same exact things. And then I tried rearranging using algebra, but unfortunately nothing came out to my demand. So I had to think a little bit deeper. I thought that, well, the mathematicians said they used the Cauchy's mean value theorem. Again, I don't know how they did so, but I remembered that infinity isn't a necessary. It isn't a finite number, which is pretty obvious by the term infinites. But in fact, it's not even a number at all. It just represents the concept of going on forever. So that means if I have a closed interval, and I say closed because I'm gonna say that a is b, a of b. I'm gonna say unbounded on the right side, simply because b is representative of infinity here. Then, if I take the mean value theorem, any smaller or any large number, there will always be a large number ahead of that. So essentially, B contains all sets of real numbers from A to B. So that is pretty interesting, because now we can establish something. So we're going to do F over A minus F over B. Now, in my paper today that I wrote down, I remember it, I switched the two terms around. But theoretically, it wouldn't matter, simply because you could just factor a -1 out on the top and the bottom. So these would be the derivatives of, oh, sorry, this should be g, g of b. This would simply be g of b over g of a, where these two terms would technically include c, which would be the number that makes them converge to infinity. So that's pretty interesting, right? Because, oh, sorry, that should be an f, actually. Because infinity is like, how can you have a bigger number than infinity? But you have to realize, for every number that's approaching infinity, there's always a bigger number than that. There is no biggest number. There's always a bigger number, bigger number, bigger number. So theoretically, this set arbitrarily contains every single number in existence. And that's how I was able to use it here. F of A is equal to 0, because remember that this is technically the interval 0, infinity. So 0 minus infinity over this, which is just negative infinity, which these two cancel out. Not the negative infinities. In fact, let me just show you the logic. Oh, shoot. Sorry. There we go. These just cross out, giving you f of A minus f of B over g of A minus g of B. But note that g of A and g of B, g of A and f of A is just going to equal, is going to be equal to 0. In fact, I probably should have said that any number that makes f of a 0, or f of a equal to 0. So that would just be an arbitrary number. It doesn't matter because b is always greater than that number. So in fact, a wouldn't be infinity here. It would simply be any number that makes f of x equal to 0. But I know there's some functions that f of x doesn't equal to 0. And yeah, so that means that this is the same exact thing as negative infinity over infinity, or negative infinity over negative infinity, which is exactly the same as the indeterminate form, which means that this is the exact same thing as limit as x approaches infinity of f of x over g of x. So by definition, these two are the same exact thing, and that's how I was able to prove it. But yeah, it is a little bit complicated. I guess I was thinking polynomial here, because any polynomial without a y-intercept will always just equal 0 when plugged in. But then I'm thinking about x squared plus 1, in which there are rare exceptions. So I guess this proof would work if f of x has a root. But again, it's just any arbitrary number that makes f of x equal to 0. So yeah, that's essentially the proofs or the challenge that I came up with. So I wonder if anyone can critique it and prove me wrong. So